So let's continue our review of time value with, I refer to them as curveballs, right? Something that's different. We're going to change the story a little bit, see how that complicates life, what it does to our decision making process. So, the first thing we want to talk about here is something called a perpetuity. The strict definition of an annuity is it's a cash flow, an equal cash flow for a certain period of time. Perpetuity is an annuity. The time frame for this is infinity. Now, the first question we have is, well, I need to know the period. So, how many years do I put in for annuity? The answer is you don't need that for the formula. It's a very simple formula. You just take the cash flow and you divide the cash flow by interest. So there's also a growth version of this, but this is how we calculate the present value of a perpetuity. So here we have an example where we need $2,000 a year to support a position. The endowment of this university earns 10% per year. How much does this investor, how much do they need to give or contribute to the university so that they can get $200,000 a year? Well, we also add, what if inflation's 3% so we can keep up with inflation? So, what data do we need? Well, we know 10% is interest. Time, we don't know time because time is infinite here. So you don't need that. Again, it's not part of the formula, so we don't have to worry about it. We don't have to worry about this y. It really doesn't influence this formula. Payments, $2,000. So they're going to receive $2,000. And we had a 3% growth of perpetuity here. So without covering inflation, we would need roughly $2 million. So $2 million a year, if you earn 10% each year, would give you $200,000 a year forever. Essentially, it assumes kind of an interest-only payment. So as long as you earn 10%, you'll always get $200,000 in revenue, and that's the contribution to the university. If we included inflation, though, they would need to contribute $2.9 million in order to cover the cash flow of $200,000 growing at 3% per year. Now, the next complication, let's talk about this compounding frequency. Again, there's only certain numbers that this can be: 1, 2, 4, 12, 365, and in some strange instances, it could be 26. If we compound more frequently, every time interest is compounded, that interest grows for the duration of that investment. So it grows compounding. Interest is earning interest. But that now requires us to think a little bit deeper. The nominal or the stated annual rate, that's the IY, right? Interest per year. Even if you divided it by the periods per year, that's the interest per period. Now, the effective true annual rate, EAR they have here, that is the annual interest rate that is compounded. The formula, you take 1 plus, again, the periodic interest rate, but you take it to the mth power. This will then compound at a different rate. So if we have a 12% interest rate compounded once a year, the effective interest rate is 12%. If we compounded monthly, 12 is the number you embed in the compounding frequency number. Now the effective interest rate is 12.683%. So I think it's better to kind of see this with an example. So let's look at this example. I purchased, I zip by the example. So here is an example. So if you invested $1,000, if you invested $1,000 for 1 year and it earned 12% interest compounded annually, you would end up with $1,120. 12% of 1,000 is $120. That effective interest rate is 12%. But what if you could take the same investment, but that investment earns interest monthly? So you change the compounding frequency to 12. The future value now is $11.26. You have an extra $6.83. So what that reflects is, since it's the same investment, the same return, the same time frame, but you have a different amount in the end, that implies the effective interest rate is different. You earn something different, 12.68%. So let's look at some other applications. You can solve for return. You bought something for $12.50. It's now worth $3,000. You bought it 4 years ago. Again, now if you leave the interest rate blank, over here it will solve for the interest rate. In this case, this investment earned 24.47%. Again, the application of this time value stuff is very mechanical. You find the numbers, you put them in the cells, or you put them in the formula, and it solves the formula for you. You want to solve for time. Again, leave time blank. How long does it take $1,000 to grow to $2,500 at 8%? Again, go through this fairly quickly, but it roughly takes 11.91 years for that to happen. Now you can do a shortcut for that. Basically, it's something called the rule of 72. It's an approximation of how long it takes money to double at a certain interest rate. At 8%, how long does it take to double? Well, $1 turns into $2 at 8% in roughly 9.01 years. And of course, 8 into 72 is 9 years. How can we apply this time value of issues to loans? Most loans that we make that require monthly payments are referred to as amortized loans. So this basically says that the payments are equal, but at the end of the loan is all paid off. So there's nothing owed after the end. So that implies each payment has a portion of it that is interest and a portion of it is principal. And I'm sure we've talked about this many times in other places, including in your own personal finance, where you think about buying a car or mortgage. How do we come up with the payments? So here's our example. You borrow $6,000. 4 years is the payment plan. Now we're going to make this a little simpler and say we're only going to make one payment a year, and the interest rate's 10%. The payment is $1,892.82. The amortization schedule that's found in this spreadsheet basically says what? The first payment, you make $1,892 at the end of the first year. $600 of that was interest. $1,292 was principal, which means now you only owe $4,707. The next year, payment's the same. Interest is based on the balance. Since the balance went down, the interest went down. Since the interest went down and the payment's the same, principal increases. In the end, we see that what? The last payment pays off the loan in full. Why is this so important? Interest expense is tax deductible to a corporation. The principal is not. Now the principal, the loan itself, you're not writing off the loan, but we do depreciate the asset. So the asset does get written off, but we don't depreciate the asset and write off the principal of a loan because they're the same, the same things. You'd be essentially kind of double dipping, if you will. The last thing to talk about is the mixed cash flow concept that we talked about. It's just a different kind of a cash flow. And again, what we find is there is a spreadsheet where you plug these numbers in. And the idea is at 13%, what values can we calculate with these expected cash flows? What's the future value? If you received $80,000 in year one, and you invested it and left it there for 7 years, in year two you did this, you keep investing these things, it would grow to $292,000 odd dollars. What's the future value of? That's the value. That's the present value. If you bring these all back, that's $292,000. If you invest and move forward, that's $688,000. If this new product line cost $250,000, what return did you earn? Or what's the net present value? Well, in this spreadsheet, you'll see that there's a thing called internal rate of return. That's the return. If you plug in here times 0, negative 250, that's the investment. Internal rate of return is 18.6%. The net present value, $42,000. Now, we'll talk about these in later chapters. But this is the kind of valuation analysis that we do when we talk about doing corporate projects. So that's the end of our videos with our review of time value of money. If you have questions, again, you can always go to the YouTube library, and if you have questions about solving for the loan amortization, it will take you through step by step how to calculate those things using the spreadsheet that I provided for you for the class. So, look forward to talking to you next time. Bye-bye.